So you see the subtitle here of the chapter of factorial design. The subtitle is Psychology is Hard. And that doesn't come from your textbook, of course. That'd be a silly subtitle. But it's true, and I think it's illustrated here. You know, sometimes people make the distinction between hard and soft science. I've had to deal with this my whole life as a fellow who's kind of half biology, half psychology. And I'd be taking, my chem classes in grad school, and taking med school classes with the med students, and they would hear that I was in a psychology department, and they would kind of derisively refer to psychology as a soft science. And I knew what they meant. They were, saying it's, not as mathematically driven or as difficult or as challenging, perhaps, as chemistry or physics. But between you and me, it's bullshit. Psychology is the hardest science. It's the hardest science because it's the most complicated topic. In the laws of physics, quantum electrodynamics is complicated for sure. But it seems like there are laws, right? And we've been figuring out those laws. Smart people have been figuring out those laws. We don't have a lot of laws in our behavior. So figuring it out is a lot more complicated. And I think this chapter provides us for the first time a tool that helps us kind of recognize that. And that tool is factorial designs. Factorial designs are research designs in which there's more than one independent variable, more than one factor. And if you're trying to figure out what caused a behavior, you bloody well better have a factorial design. Because there isn't, not in the real world, any behavior that can be perfectly predicted as a function of one single variable. We're more complicated than that. Behavior is more complicated than that. So factorial designs are kind of our entryway into the grown-up science of psychology. Factorial designs are complicated though, just like the topics we use to study them. But it's actually kind of interesting. We have to work our way through some vocabulary and some convention, just the way we do things and explain things and describe things. And it's a relatively brief chapter. After that, we just need to practice the hell out of it. So we will. Well, let's talk about it. Look, as I said, psychology is complicated. And if you want to understand a behavior or any dependent variable, you're going to need to investigate multiple variables. And what a factorial design allows us to do is to study more than one independent variable's effect on a dependent variable at the same time. We're going to see that not only is efficient, but it also gives us the ability to understand how those variables might interact. But it could be 2, it could be 3, it could be 4 independent variables, which we're going to manipulate to see its effect on our dependent variable. That said, as you can see, there's 3 basic ways this can play out. The first is kind of the pure version of this, in which we have 2 or more independent variables that are manipulatable, meaning this is a true experiment. We can assign our participants to be exposed to one of multiple levels of 2 or more independent variables. It gives us the most ability to determine causal inference. But as we've learned, not every variable can work that way. So we can have quasi-experimental factorial designs, in which our variables are quasi-independent variables, IVs that cannot be truly manipulated, and therefore we can't truly assign our participants to it at random. These are typically subject characteristics, and you've proposed a number of experiments using these kinds of subject characteristics of your participants because they're interesting. You're interested in gender differences, you're interested in geographic differences, you're interested in age differences. These are all important and interesting variables, but they are variables that we can't manipulate. And therefore we can't randomly assign, and therefore we call them quasi-IVs. You can have multiple quasi-IVs. What's the most common, though, probably is this third option, the hybrid factorial design. And just like you'd imagine, this is when at least one of your IVs is a true independent variable, one that you can manipulate and randomly assign to, and one is quasi. And this happens a lot. So you might see an IV that is manipulatable, like a drug dose, for example. And then you have a quasi-IV like age. You can't manipulate age, but you want to see its effect. You can manipulate the dose of the drug, and so now you have yourself a factorial design. The thing about factorial design that makes it a little bit complicated is the statistical notation and the jargon, just the simple vocabulary of factorial design. So I want to spend some time kind of working our way through it.
Hello and welcome to the Psych Files. Michael Britt here, and this is episode 45. And this topic is basic research design. Yes, we're going to talk about some basic research models used by all scientists, but of course by psychologists. I want to introduce you to a couple of basic designs and do so with a very interesting website I just happened upon. And I thought, oh, this is kind of a fun site. And I really have nothing to do with the site. And so here it is. It's called Hair Mixer. You get a couple of random celebrity photos. And so what you can do is you just press a button and it will mix the faces together. And they've got a whole library of faces in here. I thought, oh, this would be sort of a fun way to talk about research. So I did a little mixing of faces, and that was kind of fun. But you can also do this. You can upload your own photo, sort of make fun of yourself. So I'm just going to upload a picture of myself. I click Submit. And there's the picture of me, the one that is on the website. And you can just change these little boxes right here. Now, instead of mixing myself with Oprah, I found an interesting picture of someone that I thought, oh, this would be kind of fun. So I wondered to myself, well, first of all, I wondered what I would look like with a little bit of hair. And then I saw this picture of Anderson Cooper from CNN. And I thought, now there's a guy, nice head of gray hair. So I just decided to mix the two and to see what would happen. And luckily, because sometimes this works well and sometimes it doesn't work so good. But as you can see in this one, this worked out pretty good. There I am with some, that's gray hair there. That's not bad. Looks very distinguished. How does this relate to research design? What is it about gray hair? Think about the news. There's a certain credibility that we give to people with gray hair. Well, why not use that in a research design? So let's just go right here. Here we are. This is our basic experiment. I'm going to compare this picture of me here. There you go. That's going to be my one group. I'm going to get subjects, and they're going to look at a picture of me looking like this. And then a picture of me looking in another group, that is, going to get a picture of me looking like that. All right, so what I'm going to do is I'm going to manipulate, in this case, what's called the independent variable. Okay, that's the thing that we manipulate. In this case, I'm going to call it hair type. All right, so I'll get myself a whole bunch of subjects, and I'm going to have them sit down and take a look at this picture. And then what I'll do is I'll also make up a paragraph of text. Let's say it's a statement on the dangers of global warming. Could really be anything, but that'll do. And then what am I going to measure? Well, what effect do I think that the gray hair will have on my subjects? Well, I think the effect is that it will make them think that I know what I'm talking about. Right? So I'm going to measure something, I'll call that credibility. I think that the gray hair gives me credibility. So that's my dependent variable. Now, credibility is the concept. How exactly are you going to measure that? In other words, what is your operational definition of credibility? And so these could be established scales. I could observe people's behavior. But in this case, a very doable study, I'm going to ask people to rate the credibility of this person after reading this statement and looking at this picture on a scale of 1 to 10, 10 being very credible. All right, so I've got 30 subjects in this condition, 30 in that condition, and this is also called a between groups design. All right, I'm going to be calculating a mean based upon their answers to this scale. So what I'll do is I'll give some hypothetical results here. Since I'm predicting that there would be a higher mean score for the me with the gray hair, I'll give myself, let's say something like a 8.2 there. And me, ordinary looking, me without the gray hair, a 6.3. All right. Now, by the way, there is a confound in this study already. And I'll wait till the end to tell you what it is. In general, the study's pretty good. Okay, but there's a problem, so I'll let you know in just a minute. Okay, so independent variable, hair type, dependent variable, credibility. There's my results. How do I measure it? Got to measure it with a statistic called a t-test. Okay, a between groups t-test. All right, so I will show you the hypothetical results to this, and there they are. This is what it might look like, assuming the results came out as I just described. You've got the taller histogram here. Well, the whole thing is a histogram. The taller bar on the right is me with the gray hair, and on the left, you can see that on the left, the no gray hair, the bar is a little lower. So usually when we graph results from experiments like this, the independent variable is along the bottom, like that. In this case, hair type, really, or presence or absence of gray hair. There's a number of ways to word it. And the dependent variable is along the left. All right? And so it's pretty straightforward. Is it a significant difference? Then what we would have to do to determine that would be to analyze the data. Actually, analyze the data using the t-test. Okay? So that is really all there is to the basic between groups design. You would need two conditions. One of these you could call the me on the left the control condition if you wanted to, and the me on the right the experimental. All right. Okay. There's one other little twist on this before I tell you what the confound is here, and that is that if you can't get 60 subjects, there's another way to do this study. Suppose you can only get 30 subjects. Okay, you don't have 60 people you can get a hold of. Well, if that's the case, then what you could do is use those 30 subjects twice. So instead of this being a between groups design, it's called a within subjects design. So in other words, the 30 people come on Monday, and they look at this picture, they read the statement about global warming, they give me a credibility rating, and you say, thank you very much. Can you come back in whatever amount of time you think would be good? Suppose if they come in the next day, if you ask them to do the exact same thing, they might say, well, this kind of looks like the guy I saw yesterday. They might figure out what's going on here, which you don't want them to do that. Also, if they read the paragraph twice, they would recognize what it is. So you spread this out a little bit, give people time to forget, or you give them other tasks to do, and this is in the middle of that task, so that they don't really remember having done it that well. They certainly don't remember what number they gave on your scale of 1 to 10. Okay, and so if you did that, you save a little bit so that they come in once, they see this picture, give you a rating, come back 2 weeks later, see this picture, give you a rating, and now it's the same subjects. That has some advantages, as you can tell, with the lower number of people that you need, and the statistics also give you an advantage there. All right, so that's the within subjects design. One more twist, again, before I wrap this up, and that is that you don't have to have just two conditions. You could, for example, go back to goodoldhairmixer.com and do what I did, which was to mix yourself with someone who looks quite a bit different from you. And so here I am with some guy, I don't know who this was. This was some celebrity, but he had a great head of hair, so I thought I'd have a little fun. And so there I am with this wild hairdo here. And so now I've got 3 groups, and there's nothing wrong with that. I would probably do this as a between groups design if I had a choice. And now the problem, of course, is then I'd need 30 subjects over here, and 30 here, and 30 over here. So it's getting a little bit harder the more subjects you add. If you went down to 20 subjects, you'd probably be okay. Depends upon what you're doing this for. But if it's just for a project in class. 20 subjects would be fine. I wouldn't go too much below that. But I might predict in this case that I'm still going to give Mr. Gray Hair the highest credibility. But a guy with this much hair, I don't know. I might think that guy, he's too swarmy looking or something. So I think my subjects are going to give him a lower rating. And I think I'm going to keep my 6.3 rating next to Mr. Regular looking me here. And so this is a 3-group design, okay, 3-group between subjects design. And what I would have to do, though, is I can't use the t-test anymore. Got to use the old ANOVA. Right? It's a different statistical test, but that's what you'd have to use in this case. And that's why you have to learn statistics along with research methods, so you know what you're doing when you analyze the results. Okay, so that's it. Those are some of the main terms and ways of doing a basic research. I've done it with pictures. This could just as easily be medications, medications for depression, medications to lower cholesterol. It's the same research approach each time. Okay, but here's the problem with this study. And hopefully you've seen this. Maybe you've seen what's going on here. Remember that in a research study, you want to manipulate, that is, change or have different, only one thing between the conditions. Just one thing. And you'd ideally like everything else to be the same. Now, while it's great that these 3 pictures all have the same me, the same center of my face, same facial expression, and while it's true that I have gray hair here and brown hair here and almost no hair there, the other problem, though, is that we are all dressed differently. The confound here is that if this me here on the right gets the highest credibility rating, maybe that is due to the fact that I appear to be wearing something of a formal outfit here. Okay, whereas over to the far left, I'm dressed somewhat casually. So maybe the more formal dress is what caused people to give this picture higher credibility ratings. Maybe it had nothing to do with the hair. And this guy in the middle, obviously he's very casually dressed. And the other problem is that look at all this stuff that's going on around him. There's even a person in the background here. And then there's something that says extra, which I believe is a TV show. Maybe you watch that. Maybe you don't like this guy because you're distracted. So that's an issue that we might call that noise, because you don't know what effect that will have. You have a good sense that this formal dress is a problem. That's a confound. The rest of this is kind of noise. This is also a black and white photo on the far left. These are 2 color photos. This one's got a sort of a strange line going through it here. The ideal way to do this actually might not be to use Hair Mixer, but of course something like Photoshop. Right? That way you know exactly what is being manipulated. But if you're not a whiz at Photoshop, then do something like Hair Mixer. Have a little fun with research. Learning it doesn't have to be dull. It can be interesting. It gets serious when you get into doing research on very important kinds of studies, like those with medication, psychological treatment, etc. This could just as easily be something like a comparison between exposure therapy and EMDR. Right? 2 different conditions, different subjects, different treatments, different dependent variable. But that's how it's done. Okay, there you go. That's this week's episode on research design. And thanks for watching. And I hope you enjoy these occasional video episodes of the Psych Files. www.thepsychfiles.com. Take care.
And in a lot of ways, the notation of factorial designs is the key. The key to understanding it, and certainly the key to explaining and communicating them. It turns out we can summarize a fairly complicated study in a very simple way by using the notation of convention, meaning the way we've always done it, the way we've designed to talk about these studies. So if we have IV1, that's a single experiment. That's a simple experiment. It could have multiple levels. Don't worry about that yet. We're going to make it factorial by adding a second independent variable. So we have IV level 1 and IV level 2. And when we have multiple IVs, what we do is we say IV1 times IV2. That's kind of the way we talk about it. And we actually write it, IV1x, IV2. And in fact, you could have a third. So this could be a factorial design with 3 independent variables. Now, we don't write IV1, IV2, IV3. What we actually write is the number of levels. So if IV level 1 had 2 levels, we say 2 by, x we say by. Then IV level 2, it also has 2 levels, 2 by 2. And then IV level 3, it has 3 levels. So we call this a 2 by 2 by 3 design. It indicates the number of levels of each individual IV. And it also tells us how many IVs there are. There are 3 because you can see 1, 2, 3. And each number of levels is indicated by that number. So the first one has 2, the second one has 2 levels, and the third has 3. And you say it like this, a 2 by 2 by 3 factorial design. These factorial designs produce a much more complicated result, right? We've been talking about we get our F obtained and then we determine our F critical and make the comparison. That's still the same, but there's more here. There has to be more because we have more IVs. So here's a new term. The term is main effect. We're going to talk about what a main effect is, but we also have to know that there's also something called an interaction. These are the 2 types of results you get in a factorial design. Now the main effect, we've been using or calculating main effects all this time, we just didn't know it. Because the main effect is the effect of a single independent variable on the DV. So all of the experiments we've been analyzing for months, we've been calculating the main effect for that IV, meaning the effect of the IV on the DV. But we are now going to have multiple IVs. And since we have multiple IVs, we have multiple main effects. Because each independent variable has its own main effect. The effect of the drug on the DV. The effect of gender of the participant on the DV. The effect of the age of the participant on the DV. Those are 3 different main effects. But we're also interested in how those IVs interact with each other. And that's where this interactions portion comes in. Interactions is defined as the effect of one variable across levels of a second variable. In other words, how one IV's effects differs as a result of the second independent variable. How do they interact? Let me show you a figure, a graph, and this will help show you what I'm talking about. What you're looking at here is an example of how one can graph a 2 by 2 factorial design. And it's kind of the classic example here. It can be a little bit complicated. I just want to walk you through this very, very briefly, and then I'm going to show you kind of how we got here. But what you see here on your y-axis is your dependent variable. That dependent variable is academic success as measured by GPA. So it ranges from 0 to 4. And you can see our graph here. The lowest score we have is like 2.6. And our highest score is like 3.9. On your x-axis, you see our first independent variable. The IV appears to be a quasi-independent variable, and it's a function of whether you come from a low-risk home or a high-risk home. I'm not sure how they defined it, but it doesn't matter for our purposes. But you can see here the low-risk and then the high-risk group. Now ignore the lines for a second here. I want you to just look at the low-risk group. You can see there are 2 numbers, 2 scores. You see a circle there, that's 3.5. You see a square there, that's 3.9. That's the scores for the low-risk group. The lines there, the difference between the circle and the square, that represents the second independent variable, which you can see the circle is lower quality parenting in your home, and the square is higher quality parenting in your home. So what you're looking at here is the low-risk group. If you are from the low-risk group and you had higher quality parenting, your GPA is 3.9. If you're from the lower risk group and you have lower quality parenting, your GPA is 3.5. That's showing the interaction between risk and parenting quality. Now look at the high risk. The first number you see is about 2.7. That is the lower quality parenting group. And then you look up at the top, the high risk group with higher quality parenting, 3.9. All of the data, the main effects for risk, the main effects for parenting, and their interaction are all here on this graph. Now, we're going to walk through an example that will kind of show you how this works, but I hope you can see that when you're looking at this interaction and this effect, you're going to have high academic success, whether you're in the low risk group or the high risk group, if you have high quality parenting. It doesn't matter if you're from a low risk or high risk background if you have high quality parenting. But if you have low quality parenting and you're in the low risk group, you have a better chance of succeeding than one who is in the high risk group. The interaction between parenting and risk assessment in your environment matters. If you're low risk with high quality parenting, low risk with low quality parenting, 3.5, pretty good. But if you're high risk and have low quality parenting, your GPA is 2.7. So we see the effect of each of these IVs, but also how they differ as a function of their interaction with each other. But as I said, there's a lot of information here, but we really don't know where it came from yet. So let's take a peek. Here's another example of a factorial design. This is a 2x2 design. So that means there are two independent variables, and each of them has two levels. The first independent variable is whether you were told the test you were taking was a test of social intelligence or a test of logical intelligence. So some of our participants were told it was a social test. Other of our participants were told it's a logic test. And as you can see, looking at these squares, there were 26 people in each group. 26 people were told it was social. 26 people were told it was logical. Okay, that's IV level 1. And you can see that here, group 1 and group 2. We can look at their scores. The 26 people who were told it was a social test had an average score on our DV of 81.3. The 26 people who were told it was a logic test had an average score of 83.1. This difference here between 83.1 and 81.3, that's the main effect for our IV1. In the olden days, this would be where we were done. We compare 83 to 81 and we say, is it statistically significant or not? But this is just the first of our IVs. So we call this the main effect for IV level 1. Let's make that go away for a second. And we'll see IV level 2. It's a quasi-independent variable. It's gender. We're using dichotomous variable here for gender. Forgive me for that. But we have group 1 is male and group 2 is female. And we have 26 males and 26 females. How did the males do on the test? Well, they had a score of 82.6. How did the females do on the DV? 83.3. That is the score on the DV as a function of gender. Males, no matter what else happened in the experiment, males had a score of 82.6, females had a score of 83.3. That difference is the main effect for IV2, gender. So what we have here on this figure now represents the main effects for our two independent variables. The main effect for type of test, 81.3 and 83.1, compare those. Main effect for gender, 82.6 and 83.3, compare those. But what about the interaction? If we put both IVs on this same figure, we can actually see how they interacted. How did males who were told it was a social test do? Well, they got a score of 79.2. Females who were told it was a social test had a score of 86.4. Males who were told it was a logic test had a score of 86.0 and females of 80.2. So within these squares, you can see where each of them meet. Male meets social, male meets logical, female meets social, female meets logical, and the scores inside the squares represent the interactions. The scores in the boxes are the interactions where they intersect, and the scores outside the box represent the main effects. And we can graph them. Here on the left, you can see the main effect for male and female. You can compare the male graph to the male graph, or excuse me, the male graph to the female graph. And then you can also see the main effect for social IQ versus logical IQ instructions. And then when you look on your right, that's the interaction. Those are the scores from within those boxes. And I want you to see this in advance. We're going to talk more about this in a moment, but also when we're together. But when we graph on a line like this, where we have both IVs and the DV on the same figure, when we see these lines cross each other, that represents an interaction. Here, take a peek at this. When you look at this figure, we have factor 1, the first IV on the x-axis, and then the second factor is represented by the lines. And then you have the DV on the y-axis, just like our previous example. I want you to notice that there's no difference between that second factor on level 1 and level 2. The scores are basically the same. And I also want you to notice that the lines are the same across the first factor. Level 1 and level 2 doesn't change at all. What this represents is an IV that had no effect. There's no main effect for IV1. There's no effect for IV2. And the lines are parallel, which means there's no interaction. Look here. The lines are parallel, which still means no interaction. But what we do see here is a main effect for the second factor, because the circle and the square are very different. The first factor didn't matter. No main effect there. But the second factor, we see that difference between a 2 and a 6 at level 1 and a 2 and a 6 at level 2. So the second IV has a significant main effect. The first IV has no effect. And because the lines are parallel, we know that there was no interaction. The third possibility is this. We can see here opposite result. We see a main effect for the first factor, because when you go from level 1 to level 2, there's a big jump. You jump from 2 up to 6.5. But you see that the second factor never differs. Level 1 and level 2 of the second factor, circle and square, are always the same. And the lines are parallel, so they don't change as a result of the interaction. So we have a significant main effect of the first factor, no main effect for the second factor, and no interaction. We can also have something like this. And when we have something like this, what we're looking at is two significant main effects. Again, the lines are parallel, so there's no interaction, but you can see the circle and square are very far apart, and the lines have a steep slope as you go from level 1 to level 2. These are the different types of graphs one can have when you have no interaction. And as I said, they are all parallel. If you have parallel lines, when you graph both of your IVs and your DV on the same graph, if those lines are parallel, you have no interaction. You can also have significant main effect for one or both of the IVs, but it's also possible that none of them are significant, as you see in D. So we're going to talk a lot about this in person because it is complicated, but let me say this one last time. If your lines cross, you have an interaction. If your lines do not cross, you do not have an interaction. So as promised, not the longest chapter we've ever had, but these tools are really important, and we're going to get lots of practice. In fact, if you've already checked it out, you see that there's an article to read this week that uses a factorial design, and there's some conceptual assignments. And it's really important that we understand these graphs that represent factorial designs and their result. And so we're going to get more practice when we're together, looking at SPSS, looking at some of those graphs, making sense of the distinction between main effects and interactions. And if you can understand main effects and interactions, then honestly, you're kind of there. You're kind of where you need to be in terms of understanding the tools necessary for grown up psychology research. Okay. I'll see you soon, and we'll talk more.